So let's continue our study of constraint systems. So last time we started to study first class constraint systems. These are the most interesting ones because that's what gauge theories correspond to in the Hamiltonian formalism. Let me remind you that the definition is we have a phase space, which is a symplectic manifold. Then we have constraint functions T alpha, and we have Hamiltonian H, and the conditions are that T alpha, T beta, Poisson bracket, vanish on sigma, and also the bracket between T alpha and H vanish on sigma. So what is the geometrical meaning of this? Or physical if you want. So the meaning is that if we consider vector fields R alpha, which are for consistency with notations which I'm going to introduce, let me put twiddle here, not to confuse. So R twiddle equal to T alpha Hamiltonian vector field generated by T alpha. This R twiddle are tangent to the constraint surface, to sigma. Why it is so? Because R twiddle alpha acting on T beta, so on a function vanishing on sigma, again vanishes on sigma, right? So if we move, so what is the meaning of vector field? It's like a direction at which point. So if we move along this R twiddle and we apply this transformation generated by R alpha to our, so this is sigma, for instance. If we pick a point at our sigma and then we consider the floor generated by R alpha, for some particular alpha, then we see that when it acts on a function t, it remains 0 on sigma. So it means that we stay on the surface, right? So that's why I'm saying that R twiddle are tangent to sigma, because the floor generated by R alpha, this floor preserves sigma. So this is a transformation we are going to see. This is precisely one of possible way to see what gauge transformation is. So this is a gauge transformation. It preserves the constraint surface. The second condition, which is that Hamiltonian commutes with first-class constraints on the constraint surface, means that a Hamiltonian evolution, so the vector field VH, well, let me also put twiddle for consistency with later, which is defined as a Poisson bracket with Hamiltonian. For some reasons I changed sign, so I put Hamiltonian in the second slot. So this VH twiddle is also tangent to sigma, which means that if we study our evolution, and if we start with a certain point on sigma, then our evolution takes us somewhere, but still we stay on sigma. So evolution preserves sigma, which is precisely the consistency condition of our equations of motion. Let me recall you that equations of motion of a first-class systems are z dot a, these are phase space coordinates, equal to z a with h plus z a t alpha lambda alpha and t alpha equals 0. So this guarantees that we must stay on the surface. But in fact, if the system is first class, then if our initial point of our evolution belongs to sigma, then this constraint is preserved in time. That is why we don't get further consistency condition by considering this. Do you remember, right? Because we consider this t dot alpha, we substitute the first equation in here, and we get that on sigma it is 0. So the constraint is preserved. This is quite in contrast to second-class constraint systems, where the consideration of analogous consistency conditions led us to non-trivial equations, which were enough to express Lagrange multipliers lambdas in terms of other variables. Also, to make link with notations just introduced, we can write the first equation, I do it below. Z dot A is equal to V twiddle H Z A minus lambda alpha R alpha Z A, right? It's just a rewriting using the definition of V twiddle and R twiddle. Okay, very good. So, as we already started to discuss last time, so the crucial feature of the first-class constraint system is that even if we start with a fixed point of our constraint surface as initial data, our initial data must satisfy, so this is T alpha equals 0, must satisfy constraint equation, right? Otherwise, we can't even speak about solution of our equations of motion if the very first equation is not satisfied. It is algebraic, it's not differential. So there are initial data which solves this, which satisfy this equation, and there are initial data which do not satisfy. And we can't start. Well, we can start, but then such a solution doesn't exist, right? So we need to start with a point. This point corresponds to our initial data. We need to start with a point of a constraint system and study its evolution. But the crucial thing is that lambda alpha are unconstrained. And these are functions in time and generic functions in time. Our equations do not impose any conditions on lambda. So it means that we can pick any function lambda and then solve our equations of motion. And because our equations of motion are just first order ordinary differential equations, solution exists at least locally. So we get, for each lambda, we get a different trajectory. And there is an infinite amount of trajectories solving infinite amount of solutions to our equations of motion. And they're parameterized by initial data, but this is fine. This is always the case if we speak about Hamiltonian mechanics. We start with any initial data and we get a unique solution of our equations of motion. So our solutions are parameterized by initial data. But in addition to this, we have a huge arbitrariness, functional arbitrariness, corresponding to these lambdas. And this is precisely the gauge freedom. So there is a huge arbitrariness in our solutions, which is not physical. So the idea here is that all solutions with zA of 0 equal to certain, so which have same initial data, but corresponding to different lambda alphas, are physically equivalent. Or in other words, they are related by gauge transformation. So gauge transformation, it's a very dangerous term because sometimes it's depending on formalism and language. It's used in a slightly different way, but the idea is, of course, always the same. So if we speak in terms of solutions to equations of motion, then gauge transformation is a transformation which takes one solution and brings it to an equivalent solution. In this case, of course, we need to speak about solutions satisfying certain initial data. Strictly speaking, of course, we can also allow for slightly different initial data, which are also going to be physically equivalent. This corresponds to a gauge transformation of our initial data. So let's study this in some more details. So what we are going to check is that, in fact, evolution respects just one moment. I forgot to introduce one important notion. So let's introduce the notion of gauge orbit. Again, this term in different formalism can be slightly different. Again, idea is the same, but in this Hamiltonian context, gauge orbit containing point P in sigma in our constrained surface is a set of points which you can reach from P by considering gauge involution. Points that can be reached by z dot A equals to minus R of z A, and here my lambda of T. So I forget about real evolution. So you remember, in our equation, there are two terms. The first term, roughly speaking, corresponds to genuine physical evolution generated by Hamiltonian. And there is a second term, which is like gauge evolution, which corresponds to which is generated by constraints. So we want to concentrate on the second one and forget for the moment to disregard the first one. So let's just consider pure gauge evolution determined by lambdas. So by solving this equation, we can get to, so we start with a certain point and we can get to different points here and there, and all these points form a certain subset, and this subset is a gauge orbit. So a gauge orbit containing point P is a collection of points of sigma, because we know that this evolution preserves sigma, so we can safely forget about the rest of our phase space, and we are going to see to which points of our sigma we can get by the floor generated by this equation, right? So we pick our initial data. So z a of t is z. Well, let's identify coordinates and points is our starting point p, and then we get somewhere. Our points start to evolve, and collection of all these points which are reachable by this is called gauge orbit. And somehow it resembles a little bit the notion of orbit of a group. So in some sense it's an orbit of a gauge group, but again this terminology very much depends on the context. So let's not introduce concept of gauge group for the moment. Okay. So, and then this physical interpretation should be that all physical states represented by the gauge orbit are equivalent. So in fact, it's like degeneracy in description. So physically, we only see the equivalence class of states. So classically, points of our phase space are classical states, right? For the moment, we're not talking about quantum mechanics. We are just talking about classical theory. Like in usual Hamiltonian mechanics, a point of phase space is a classical state, right? Because if we fix this point, we know everything. We know future evolution, we know values of all observables, we know everything. That's why the physical state of a Hamiltonian system is represented by points of the phase space. Now we go to unusual Hamiltonian systems, which are first-class constrained Hamiltonian systems. There are two differences. First, not any point of our phase space represents a physical state. This is because we have our equation T alpha equals 0. We must stay, physical states can only belong to the constrained surface sigma. So not all points are allowed, but even worse, if there are 2 points like this and this on the constrained surface, it might happen that they represent one and the same physical state. They are physically indistinguishable. This leads to the concept of observable. Again, in usual Hamiltonian mechanics, observable is just a function on a phase space. Because if we know a state of the system, we can measure whatever we want. And measuring means that we associate to a state a number. And this rule, which associates to a state, to a classical state of the system, the respective number, is precisely function, right? So if there is a rule which takes points to numbers, then we are speaking about function, right? So how this concept changes if we discuss constrained systems. So first of all, our true observables can only be functions on sigma, right? Because it doesn't make sense to speak about states which are not which do not belong to sigma because they are not allowed by our dynamics. So our functions should also be our observables should also be functions on sigma. But again, same picture. So if there are 2 points, 2 states, which belong to the same gauge orbit, then we can't distinguish these 2 physical states by the measurement, because whatever we measure, the result should be the same. What does it mean mathematically? Mathematically, it means that observable should be constant along the gauge orbit. So it should take same value at all points of the same gauge orbit, and this should happen for any gauge orbit. In fact, for this, it's enough to require the following, and this is a simple statement. So let's do it as a definition and then prove the statement and then prove that it is constant. So f from functions on sigma is an observable if R alpha f is 0. Here, R alpha is a restriction of R alpha twiddle to sigma. That's why it's very convenient to work in terms of sigma. That's why first I introduced the Hamiltonian vector fields generated by constraints as R alpha twiddled, and then I reserved the untwiddled version of the same notation for a vector field on the constraint surface, which is just a restriction. Recall that these guys are tangent to sigma. That's why restriction is well defined, right? So we are talking about functions which are annihilated by these vector fields. And in fact, the idea is of course quite clear, because these vector fields R alpha are precisely the ones which are tangent to the orbit, right? Because our orbit is generated by the floor of these vector fields R alpha. So let's do it as a statement that Rf is constant along the gauge orbit. Along any fixed gauge orbit. The proof is very simple. So we recall the definition of gauge orbit. It is just this thing, right? I should have put twiddle here. So it's an evolution which is generated by vector fields R alpha with certain coefficients lambda alpha of t. And we forgot about Hamiltonian, the genuine evolution. So if you want to see what f dot is, how f evolves if we go along such a floor, we compute it, and it happens to be df over d. Let's introduce coordinates. Well, let me still use z, but now think of them as coordinates on sigma on constraint surface times z dot, which is R alpha acting on z a, and all this is multiplied by lambda alpha of t, right? But this is nothing but lambda alpha of t R alpha acting on f, and this is 0 by definition, or by the above definition of the observable. So if f is annihilated by R alpha, it's going to be constant along any path generated by this gauge transformation. this flow generated by this equation for certain particular functions lambda alpha. Okay. So what is so this is fine, but what is not yet clear? It's not yet clear if this definition is actually compatible with evolution, because for the moment we forgot about Hamiltonian. But if we have a Hamiltonian, then the evolution is not just a gauge transformation, right? We also have a different trajectories which apparently take us outside our gauge orbit, because Hamiltonian is not supposed to preserve gauge orbit. And to make sure that our concept of our definition of physical states, of gauge orbit, of evolution, that everything makes sense, we need to give a meaning to the evolution, right? So the consistency is that if we start with a point, with a certain physical state, then it, no matter which lambdas are picked, because they're completely free, we should get to the same gauge orbit after a certain time t, right? So let me make it more precise. So our evolution is z dot a equal to this. Now I stay in z a minus lambda alpha r alpha z a. This is our evolution. It's already written in terms of, we assume that zeta now coordinates on sigma only, because the dynamics outside sigma is irrelevant. So we know that if we forget about the first term, we just stay, if we drop the first term, we just stay in the same gauge orbit. Now we add the first term because it's important, it's a physical evolution, and we want to make sure that irrespective of which lambdas are taken, we get from, in a certain time, we get to equivalent physical states, right? So there is a concept of evolution of physical states, but our physical states are gauge orbits. They are like equivalence classes of points. So two points are considered equivalent if they belong to the same gauge orbit. So that's what we need to make sure of. Good. So what we do for this? A useful way to check it is to introduce a maximal set of observables. Maximal set of functionally independent observables. Let's call them xi. So xi are functions on our constraint surface such that r alpha xi equals 0. We know that x's are, any observable is constant along the gauge orbit. So what we can do, we can consider surface in sigma, singled out by xi equals to const I. So just fix some numbers and consider such a surface. So this surface is going to contain at least one gauge orbit. Why? Because if we pick a point from this surface, and start to and apply gauge transformation to it. So means start solving this gauge evolution equation without Hamiltonian. We know that values of observables along all solutions is unchanged. So it means if our point belongs to this surface, then values of x's at any other point of the gauge orbit are the same. So it also belongs to the same surface. In fact, because we picked maximal set by assumption, it is precisely gauge orbit, at least locally. In fact, the thing is that globally it can be quite a sophisticated geometry. So for the moment, I'm explaining ideas, and ideas are well illustrated if we assume our system sufficiently simple. So we just restrict our attention to one coordinate patch, for instance, to avoid discussing of global geometry of these things. For instance, you can get to some tricky situations like irrational winding of a torus and this sort of things. That's what we exclude for the moment. Okay, so because it is maximal, it means that any other observables, it can be expressed in terms of x, and it also keeps its value along the gauge orbit. So this means that the surface must be a gauge orbit, at least locally. And then it is convenient to ask a question: what happens to our orbit under the real evolution generated by Hamiltonian? And we know that if we consider evolution of our observables, because they determine our surface, so x dot I is equal to VHXI minus lambda alpha R alpha XI, and the second term is 0. So this is just VHXI. So the evolution of these functions, x observables, determining the gauge orbit does not depend on choice of lambda. This means that in whatever way, and at the same time, values of x, because it's a maximal set, values of x determine a gauge orbit. So if we start, again, if we are on sigma, if we start somewhere and evolve, then because xi of this point is equal to xi of this point, these 2 points again belong to the same gauge orbit. Of course, if we start somewhere here, in the same time, we again get to the same orbit. So in other words, evolution acts on the space of gauge orbit. Right? And this is a crucial space. This is called reduced phase space. Reduced phase space. Space, by definition, is a space of gauge orbits. And it's not difficult to see that because our functions x uniquely parameterize the orbit, because if we change x, it means we went to a different orbit. Xi are coordinates, strictly speaking, local coordinates, because our considerations are local coordinates on let's call it mred, on mred, right? And they are precisely the observables, and the evolution is well defined in terms of this reduced space. Its evolution is just determined by first order differential equation x dot I equal to VH xi. And VH is also well defined on this space of orbits, because we just saw that the evolution preserves the equivalence classes. So, and this is usual, in fact, with additional observation that this reduced phase space inherits Poisson bracket, and this equation, in fact, is just a Hamilton equation with respect to this Poisson bracket. We understand that we are actually talking about, again, a usual constrained Hamiltonian system, not constrained, whose phase space is very tricky. It's this quotient it's a quotient space of the constrained surface. But all the story about these constrained systems is that this quotient can be extremely sophisticated in reality, because these considerations which I just gave, they apply to finite dimensional situation, so to mechanical system, not to field theory, strictly speaking. Of course, they also apply to field theory, but then one has to be very careful with what this index I means, because it also contains spatial coordinates. Our manifolds become infinite dimensional. There are issues of locality, etc., etc., etc. And that's why we get to the sophisticated world of field theories, which are not as simple as the world of mechanical systems, mostly because of infinite dimensionality of the respective spaces. But morally, if we disregard all these subtleties, morally we are just talking about systems which give a tricky way to describe usual Hamiltonian systems, which are hidden somewhere inside as this reduced phase space. So let me also explain how can we get a Poisson bracket on this reduced phase space. So, and the idea is very physical. And it amounts to defining functions on the reduced phase space, which are true observables and equivalent observables, as equivalence classes of functions on M satisfying this condition. So we want, of course, it is clear what this condition means, because this condition gives us that R alpha acting on F restricted to sigma is 0. So this is an observable. So we can talk about observables in terms of functions defined on the entire phase space M, where we do have Poisson bracket. But of course, if we pick all functions satisfying these conditions, we get more than we need, right? Because two functions satisfying these conditions will lead us to would probably lead us to one and the same function on sigma if they coincide on sigma, right? So in addition to this condition, we need to introduce equivalence relation. That F is equivalent to F equivalent to, let me write it like this, f is equivalent to g if f on sigma is g on sigma. So sometimes it's called subquotient, right? We take a subspace of functions satisfying this condition, and then we quotient it with respect to the following equivalence relation. The two functions are considered equivalent if they coincide on the constrained surface. So if we implement this equivalence relation, we precisely get to functions on sigma annihilated by these vector fields are alpha, right? Because that's what these conditions say. Yeah, so we precisely get to the observables. So observables are functions annihilated by this. So this, what we had is a Dirac definition, what we had above. It's Dirac definition of observables. So observables are phase space functions, which are first class, so commute with constraints on sigma, and two observables are equivalent if they differ by a term vanishing on the constrained surface. So what is what we can check now? So what is above? It's precisely this Dirac definition of observables. What we can check now that in fact this quotient, which can be identified with functions on the reduced phase space, right? Because functions on the reduced phase space are precisely observables on sigma. So these are functions on sigma annihilated by R alpha. First of all, make sure that this equivalence relation, so this that sorry here. So let's first make sure that Dirac observables, let's call these Dirac observables. Dirac observables form Poisson algebra, which means that we can multiply them as equivalence classes. So we take f multiplication of the two to be an equivalence class of their multiplication, and this is consistent. So this is well defined. Why it is well defined? Because if we add, so our equivalence classes are modular, are defined modular functions vanishing on sigma. So if instead we pick a different representative, f plus, let's say, h, and h vanishes on sigma, then what we get here, we get f g plus h, g equivalence class, but h vanishes on sigma, so the second term is gone. So it's the same equivalence class, right? So we have a multiplication for this in observables. So when we know that these equivalence classes are functions on the reduced phase space, so we can see their multiplication in terms of functions on the entire phase space, right? Strictly speaking, we should also check that multiplication of fg satisfies the condition for a Dirac observable. But this is straightforward, right? You just apply Leibniz rule, and you get f t alpha, which vanishes, and g t alpha, which also vanishes on sigma. So this is fine, but this is expected because we knew that we have at least locally this reduced phase space, and on reduced phase space we have multiplication of functions. And now we just learned that we can define the same algebra as a subquotient of the algebra of functions on the entire phase space. And second, what is more interesting is that we can also define a Poisson bracket there. So we define a Poisson bracket of two equivalence classes, so which are functions on reduced space. Let's call it reduced bracket. By definition, it's going to be Fg restricted to sigma. So we, to compute a Poisson bracket, we pick representatives F and G, we evaluate usual Poisson bracket on the entire phase space, and then we restrict to sigma, or what is the same, let me better to have it in a homogeneous, we pick a equivalence class. So what is to be checked? It's also well defined. What is to be checked? Again, as usual, we need to check that nothing depends on, first of all, that we indeed get what we want, and second, that nothing depends on the choice of a representative. So first of all, if we evaluate Fg, it's again an observable. That's what we have to check, which means that if we take a Poisson bracket with T alpha and restrict to sigma, we should get 0. But now, this amounts to what? This amounts to Jacobi identity and one additional step, which we are going to discuss now. But maybe before doing this, as I need another page, let's see that nothing depends on equivalence class. So if instead of F, again, we take F plus H, and then take an equivalence class, and H vanishes on the constrained surface, then this is equal to Fg. And to see this, we need, to see actually both these statements, we need the following remark, which we had, I think, which we briefly discussed last time. So suppose that H on sigma equals 0, and also that T alpha are regular. Regular means that they can be taken as part of coordinate system, or equivalently that dt alpha over dz A has maximal rank. Then H can be written as H alpha T alpha. That's what we need. So any function vanishing on sigma can be written as something proportional to constraints determining sigma. That's what we also discussed last time, and if I remember correctly, it was an exercise to check it. So now let me get back to what we have. We need to make sure, for instance, let's consider the second, to make sure that this equality holds. But now we know that H here can be written as a combination of linear combination of constraints, and this actually does the job indeed. So let's compute H with G, which is restricted to sigma because that's what matters only, and then this can be written as H alpha T alpha G, restricted to sigma. This can be written as, using Leibniz, this can be written as H alpha T alpha G, restricted to sigma, plus H alpha G times T alpha, and all this restricted to sigma. So the first term is 0. Why? Because g is a first-class function. It means that it's bracket. You remember our definition. We call observables, Dirac observables, functions which commute with first-class constraints on sigma. So that's exactly what we get here. And this second term, everything is simple. It is just proportional to T alpha. So it vanishes on sigma by definition. Okay, so that's good. And let's check now the first one. So what we need to show that, again, if here we need to show that this vanishes on sigma. Indeed, let's do it. So f g T alpha on sigma equals to, now we do Jacobi. So we get what we get. We get f with bracket g with T alpha on sigma plus f T alpha g, right? Again on sigma. But as we saw, g with T alpha, because g is a Dirac observable, vanishes on sigma, and hence this quantity can be represented as g alpha beta T beta for some functions g alpha beta. And of course the same here. But you see, so after replacing g with T alpha with this, what we get we get exactly this type of expression. And we know that this bracket vanishes on sigma because f is also a Dirac observable. And exactly the same happens here. So what we proved that the space of equivalence classes of Dirac observables, strictly speaking, it's better to say like this, is equipped with Poisson bracket. So the Poisson bracket descends to this space of equivalence classes of Dirac observables, and this space is also in algebra with respect to multiplication. It's an algebra of functions on the reduced phase space. So we get a Poisson bracket here, and we can also write evolution. Evolution, what it is, you remember that we have, so if f is observable, we can, let's write evolution equation in terms of observables, generic observable rather than coordinates. F dot is equal to f h plus f t alpha lambda alpha, right? And then we take equivalence class everywhere, right? So what we get, the second term disappears because f with T alpha vanishes. Taking equivalence class means restricting to sigma, right? Poisson bracket of f with T alpha vanishes there because T alpha is because f is an observable. So what we get is that f equivalence class dot is just a Poisson bracket of f with Poisson bracket of h, and this is reduced, right? Or identifying f as a function on mred, this can be written as f dot equal to f with h reduced, where h reduced is just restriction of h to to the constraint surface, right? So it's a usual Hamilton equation. So if we can explicitly go to the reduced phase space, then we meet the just a usual Hamilton dynamics, which is determined by Hamiltonian H red, which is just a restriction of H to the constraint surfaces. Because H is observable, it can be also considered as a function of reduced space, and we have a Poisson bracket there, so we get usual Hamiltonian dynamics. Okay, and here is an exercise. So under the above conditions, which means finite dimensional, everything is regular, nothing special, show that M red is symplectic. So in other words, that this Poisson bracket reduced is not degenerate. This can be done, for instance, using coordinates. So let's help you a little bit. Coordinates. So what we are really interested in are object on sigma, right? Because physics sits there. So we already introduced xi, which is a maximal set of functionally independent observables, and because they're functionally dependent, we can assume that they form a part of coordinate system, and let's supplement them with coordinates y alpha, such that these are local coordinates on sigma. Okay, and let me remind you that x by assumptions are observable. So R alpha acting on xi are 0, is 0, and maximal set of independent observables. Okay, so we have a very special coordinate system. In this coordinate system, for instance, xi equals to constant such surfaces are gauge orbits, and the remaining variables y alpha, they are roughly speaking coordinates on the gauge orbits. So let's write down what our main objects are, right? So F observables. These are functions which depend on what? So observables are functions annihilated by these vector fields R alpha. Gauge generators, sometimes they are called. So what are observables in coordinate terms? Can one try to answer? Pardon?
They depend only on X?
Yes. Why? Because, of course, R alpha preserves X. So R alpha should look like this. This should be something like R alpha in these coordinates, d over dy beta. And these are some functions. They can depend on everything. But what is important is that these vector fields R alpha, they differentiate only with respect to y, because if they differentiated with respect to x, they were term also d over dx, this would violate this assumption, right? So that's what R alpha look like. So what evolution look like in these terms? Evolution is our vector field VH, which is by definition just a bracket with Hamiltonian restricted to sigma. But this one is not supposed to annihilate observables. On the contrary, it should determine evolution of observables. So this guy contains both H alpha d over dy alpha. It has components along both directions. But of course, when we applied VH to observable, we only see the first one. The first one is physical. Right? So that's what it looks like in coordinates. And in fact, this VHI is going to be nothing but dH red over dxj. So we can write it like this. If we really go to the reduced space. So that's what the picture on the constrained surface is. And let me remind you that the exercise, which requires essentially just a bit of linear algebra, is to make sure that the Poisson bracket on the reduced phase space is invertible, or in other words, that the reduced phase space is symplectic. Okay, good. The next thing we should discuss is gauge fixing. Again, this term is used in very often and with slightly different meanings. Of course, the idea is always the same, but the precise meaning may differ depending on the context. Either we speak in terms of purely Hamiltonian formalism or Hamiltonian action, Lagrangian formalism. It can be slightly, the meaning can be slightly different. In this, so let me correct here, in first class Hamiltonian systems, in precisely this setup which we are in now. So what is this? So let me again draw our main picture for the moment. So we have these gauge orbits. We have evolution, which apparently take one orbit to another orbit in a consistent way. And so we know that it's convenient to speak about evolution and other physical properties of the system in terms of the reduced phase space, right? So in terms of useful, in terms of M reduced, which is roughly speaking is a quotient space of our constrained surface by gauge orbits. So equivalence relation, so we take a quotient of sigma by the equivalent relation. The 2 points are equivalent if they belong to the same gauge orbit. But usually, if you tried such type of games, you know that it can be quite difficult to find explicitly and to work with such a quotient quotient space, it's easy to give it like general constructions. That's exactly what I do now. Let's take a quotient, it exists, everything is well defined, we go to reduced space, and this is our dynamics. It looks extremely simple once you get used to it. But in reality, it's sometimes almost impossible to do explicitly. Because to work with this reduced phase space, you need to pick coordinates there, which are only local, which are difficult to define. Everything becomes nonlinear, unsolvable. So in real applications, full stop. You can't really do these steps practically. Morally, in principle, you understand how it goes, but it's very difficult to do it explicitly, and practically it's useless to do real computations, not to develop general theory, but to answer concrete questions. This is not always, but quite often it's not a good way. And also this is even in mechanics it is like this in a way, but if we go to field theory it becomes even worse, because in field theory we usually want locality, and it may happen that this and it happens usually that this space is determined by differential equations in partial directions. So you can't even find coordinates in a local way without really solving differential equations, assuming boundary conditions, etc. So it makes everything a hell. So what is an alternative, which is it can be a little bit approximate, but it's useful, and that's what people do, is to fix the gauge. What does it mean, fix a gauge? Is instead of taking a quotient, suppose we could find another surface here. So this is gauge fixing surface, such that let's call it like chi alpha equals 0. So let's it is determined by some conditions, chi alpha equals 0, independent conditions, such that I need to give a name G, such that G intersects each orbit once and only once. So in other words, it picks one representative, 1 point, out of each gauge orbit. So what realistically we are talking about? We are talking about a particular parameterization of the our reduced space. The problem, again, in reality, is that such a surface may not exist globally. Locally, under the assumptions we made in mechanics, in finite dimensions, it exists. Globally, probably not. But if we are ready to disregard certain issues, like for instance, if the surface intersects a certain gauge orbit twice or 3 times or something like this, maybe it's not so important in the class of solutions we are interested in, we can live with that. At least it can give a fast way to compute something. And this surface is called gauge fixing surface because precisely it removes the gauge freedom, right? It picks a particular representative out of each gauge orbit, and the reduced phase space can be identified with this G. So at least locally, under the assumptions we are working on, at least locally, M reduced is equivalent to G, is diffeomorphic to G as a manifold, but only only locally. Globally, it can be not the case, and this is the cause of many difficulties like Gribov ambiguities, etc. Of course, these are not exactly Gribov ambiguities, but in Hamiltonian formalism. Okay, so what are conditions? So it's also convenient to define this surface again in terms of something like constraints, right? So we can think of this chi alpha, these guys. We can think of them again as additional constraints. So what is the condition, at least local, that a gauge orbit intersects this gauge fixing surface only once? So what has to be checked? It has to be checked that our vector fields R alpha, when they act on chi beta, you get certain metrics. Let's call it, well, it's not Dirac matrix, dl alpha beta. So what do we need to require from this matrix to make sure that that we pick at least locally only one point of each orbit? Any ideas? So let me remind you what it looks like in coordinates. So R alpha is something like R alpha beta do dy beta. So y are coordinates along the gauge orbit. Let me put gamma here because I used beta already. Function gamma. So these fields, we are discussing just one particular gauge orbit, right? So let's concentrate on one orbit. It's going to be the same for all of them. So you see these fields are alpha beta, these vector fields. They are, you can, if you pick one orbit, they are just vector fields on this orbit. So there's a vector fields on space with coordinates y, and we want that our condition, our functions chi gamma, they pick a one point of this orbit. So what does it mean? That this thing should be invertible, right? For instance, to pick one point, you should for instance take y coordinates to particular values. Then if you go with this r, and r alpha beta is invertible because otherwise it can't generate all the gauge orbit, because otherwise it's not going to have r is not going to have a component along certain direction. That is why this thing should be invertible. This is the condition. So for instance, you can pick kappa gamma equal to, for instance, y gamma. Well, sorry for the index in opposite position, doesn't matter. So if you pick, for instance, if you want to pick one point where y equals 0, this is precisely the origin of this local coordinate system, we take psi equal to chi equal to this guy, chi, equal to y, and then this condition is satisfied. But this is, of course, invertibility of this thing is coordinate independent notion. And locally, it guarantees that the intersection of our gauge orbits with of any gauge orbit with this gauge fixing surface has only one point. Globally, it's probably not the case, but we do local analysis as the simplest possible step to understand what's going on without getting into really sophisticated problems. First, we want to understand how all this works. Okay, one can think, of course, of these functions kappa. Think of kappa. Oh, why kappa? I confuse always. Chi. Think of chi alpha as functions, uplift them to entire phase space, to functions on M. Then this condition equivalent to Poisson bracket of T alpha, because it generates R alpha, with chi beta on sigma invertible. Does it remind you something? So what I'm doing, you see, these vector fields are alpha. They anyway take derivative only, differentiate only along the surface. So I can just uplift chi to functions defined on the entire phase space. That's our usual ideology. If you have something on the surface, you uplift it to the entire space to simplify life, but you need to, of course, make sure that nothing depends on the way you uplift it. But this condition does not, because R is tangent to the surface, so it doesn't matter. So I have just rewritten this condition, that this thing is invertible, that is d alpha beta is invertible in terms of the initial phase space. So it's a bracket with between constraints and chi, restricted to the constraint surface, is invertible. What does it mean? It means, in fact, that T alpha, chi beta are second-class constraints, because this guarantees that the respective Dirac matrix is invertible. If it's not clear, exercise check. Check this. These are second-class constraints. And this gives also an interesting, it gives an interesting interpretation. So if we have a first-class constraint system, which is gauge system, we can pick certain gauge conditions. So gauge conditions are precisely these chi's equal to 0, and you can think of them as defined on the entire phase space, not just on the constraint surface, because anyway we are only interested in what happens on the surface. And then our initial first-class constraints, T alpha, together with this condition chi, form a set of second-class constraints. In particular, this means that we know physical interpretation, and the physical interpretation is just that we are dealing with usual Hamiltonian system, which is defined on the constraint surface. But what is constraint surface? Constraint surface is just the intersection of sigma with gauge fixing surface. So this is precisely our reduced, at least locally, this is precisely our reduced space. So again, if we have a first-class system, we can fix a gauge, means pick these gauge conditions chi alpha, and we end up with a certain second-class constraint system whose reduced space is our required reduced space. But the subtlety is, of course, that picking a particular gauge, we lose gauge invariance, which can be very useful, or because we are again forced to work in certain submanifold. We need to pick their coordinates, or we are forced to work with equivalence classes. So it's again additional hassle. And also one suppose we study a certain system, one is working using one gauge condition and another one is using another gauge condition. Then they want to compare the results they computed. And it can be quite tricky to make sure that the results are the same, because one obtains the answer in terms of one parameterization, another person obtains the answer using another parameterization. And this is a standard typical problem of gauge independence in the theory of gauge systems. So you do something, you compute. For instance, if you need to quantize, you somehow must fix a gauge. at least in field theory. Then you need to make sure that what you computed doesn't depend on the gauge you choose, because if it does, it means you did something wrong. So that's the idea. Okay, and in final few minutes, let me say a few words about the underlying geometry. So, because this is what happens on the constrained surface is quite a typical geometrical situation, and it's good to know the language in which such situation is usually described. Geometrical picture. So to have in mind the same idea, so suppose sigma is a manifold, but now we don't care if it's a constrained surface of something or not. Manifold. Okay. And the first definition we need is a distribution. So D is a distribution on sigma if we are given with, for any point in sigma, there is a subspace of the tangent space at this point. So at each point, we have a subspace of tangent space. And you assume, this is standard, it's a part of definition, assume that dimension dp is constant. So it doesn't depend on point. It doesn't jump if you go from one point to another. Equivalently, D is a vector subbundle of T sigma, right? So T sigma is a tangent bundle of our manifold. So a fiber over each point of sigma is just a tangent space at this point, and D is just a subbundle, right? So at each point there is a subspace. It's just equivalent reformulation. But if we speak about subbundles, the condition that dimension is everywhere the same is part of definition, because otherwise it's not a subbundle. We say that a vector field X in well, usually this is a notation for vector fields, belongs to distribution, to D, if at point P, this is just an element of tangent space, it belongs to dP, to the subspace. So then we say that vector field belongs to distribution. Okay, another important definition is that of integrable submanifold of distribution D. So L in sigma is called integrable if for any point of L, T P L coincides with dP. So what I mean here, so we pick a point, so there is a submanifold, and distribution means, for instance, in this picture I can only draw one-dimensional distribution, so we have a vector at each point, right? Non-vanishing vector at each point. This defines for me the distribution. And strictly speaking, one-dimensional subspace, but this is the same as saying that we have a non-vanishing vector because it defines a subspace. And this is submanifold. So what does it mean? It means if we take a tangent space at point P, then this tangent space coincides with our one-dimensional subspace with our distribution. So in other words, if we define our distribution in terms of a vector field, then this vector field is tangent to our distribution. But of course, in multi-dimensional situation, we can't define distribution just in terms of one vector field. We define it in terms of a collection of vector fields. Okay, so this is an important concept of integrable submanifold. So the idea is we are trying to find a submanifold such that this holds. So its tangent space everywhere coincides with the distribution. So for a given distribution, integrable submanifold may exist or may not exist. It's a question of what distribution we have. But for instance, if we have a integrable submanifold of our distribution, it means that our vector field. Okay, let me do it like this. And now you will see the relation with what we were talking about before. So suppose that vector fields R alpha belongs to our distribution and generated. In the sense that at each point, linear span of R alpha equals 2 dp. That's very useful. It's like picking a basis in the distribution. dp, a linear span at p. Okay, so if we have if L is an integrable submanifold, then R alpha are tangent, right? This is precisely by definition, a tangent to L, right? And moreover, if we take commutator R alpha, R beta, and evaluate it at point P in L, then it is again belongs to TPL, right? Because if two vector fields are tangent to a submanifold, and if you take their commutator, then we again get a field tangent, or this is equivalent to that this thing equals to some numbers, gamma or gamma. Because if our vector fields form at each point form a basis, then any tangent vector can be decomposed again with respect to this basis R, right? So what we see that commutator of our vector fields at point P is again proportional to our vector fields and hence belongs to the same distribution. But all this happens at any point to L. So if there is an integrable submanifold, that at points of this submanifold, the commutator of two vector fields from the distribution belong to the distribution. And if we want our distribution to have integrable submanifolds everywhere, that this should hold everywhere. And for this, there is a special definition that D is involutive if, can you hear me? Excuse me, because something went wrong with my computer. Okay, very good. Anyway, we have to stop in a couple of minutes. Okay, so D is involutive if x, y belongs to D for all x, y in D. So we say the distribution is involutive if the commutator of vector fields belonging to the distribution is again a vector field belonging to the distribution. And as we saw, if we have integrable submanifolds going through, if we have integrable submanifolds everywhere, it means that this condition should be satisfied. And inverse is also true, and this is called Frobenius theorem, which says that D is integrable, which means there is an integrable submanifold going through each point. Let me integrable. Integrable submanifold through each point. If and only if D is involutive. So these are equivalent. And this, strictly speaking, sigma is finite dimensional. In infinite dimensions, it's not necessarily so. So this is a famous theorem. And yeah, okay, I have to stop now. So you already see the idea. So what do we have if in the case of first class system? On sigma, we have R alpha, which are restrictions of these guys to sigma. Then from the first class condition, we know that R alpha, R beta commutator is again proportional to, for some functions, U R gamma, right? Because we know this, well, maybe this, let's leave it as an exercise. So of course our constraints are regular. This is an assumption. Prove this. Prove this equality. So in other words, it means that because any vector field is a combination, any vector field of our distribution is proportional to R. We can given R, we generate distribution, and this distribution is involutive precisely because our constraints are first-class constraints. So exercise is to show that D is involutive if our constraints T alpha are first-class constraints. Okay, thank you very much for attention.